Hello and welcome to Strange Loops. Today I wanted to discuss a device called a planimeter. Now, a planimeter is a mechanical tool that can calculate the area inside of closed curves. And the way that it does this, and the reason why it's pretty magical, is by tracing around the perimeter of this curve, it's able to actually calculate and derive the area. And so in this video, I want to do three things. First, go over the history of why and how the planimeter was invented. Second, go over the components of an actual planimeter and demonstrate how a planimeter is used. And then third and finally, delve into the mathematics behind the proof of why a planimeter is able to work. And I have to say, the result is absolutely lovely, and so I hope you stick around. With that being said, let's get into some history. The idea of a planimeter traces way back to around 1814 and was invented by somebody named Johann Martin Hermann, who was working as a land surveyor in Bavaria. Now, his job was to map boundaries and dimensions of parcels of land, and built this device to help him calculate area of complicated land plots, which, based on this, it looks like there might have been a lot of. Before the invention of the planimeter, calculating area of an irregular shape was pretty laborious. Most commonly, people would try to subdivide the area into smaller areas of triangles or rectangles, shapes where the area could easily be calculated. People also used transparent grid overlays to try to calculate the number of grid cells contained within the area of the shape. And probably my favorite method was where researchers used something called the cut and weigh method. For example, they would have a map with a known area, and then cut out a parcel of land which they didn't know the area of, and weigh this in comparison with the original weight of the map, and be able to calculate the area based on that. The planimeter really took off when a Swiss mathematician named Jakob Amsler created a version called the polar planimeter, which was cheaper, more practical, and accurate. And this is the type of planimeter which I'll be showing you today. As you can imagine, having a tool to measure the area of an arbitrarily complicated closed curve had all kinds of use cases. In World War I, for example, a couple of French scientists used planimeters to measure the progression at which wounds healed. Charmingly, botanists also use planimeters to measure the leaf size of strawberry plants by tracing out a leaf on a sheet of paper and then calculating its area. So here's a little prototype polar planimeter that I 3D printed. And it's not the best 3D printing job, but I will attach the 3D model in the description. And if you're curious, you can definitely try to 3D print one yourself. So I'll first go ahead and explain each of the components of the planimeter. And one of the good things about the planimeter being so cheaply made is that it comes apart a little bit too easily. And so we'll get rid of this component for now and start with this component, which is called the pull arm. And so the pull arm rotates around a fixed point. So here I just have a paperclip sort of thing, and you can see that the pull arm rotates around like this. And so it can go anywhere within a radius of its length around this fixed point. Next, we have this tracer arm, which can rotate around the joint at the end of the pull arm. So we attach it like this, and it can rotate around anywhere here. And so you can see with both of these joints, that gives the tracer arm a lot of flexibility. And one interesting question might be to ask, well, actually, where can the tracer arm reach? So where can this point, the end point of the tracer arm, reach? And it turns out that the shape that it can reach is called an annulus. And so you can imagine at its very far extent, which we can't quite see, maybe I can orient a little bit, it can reach to all of the points in a circle of radius of this length plus this length around it, and then can rotate of any of those points in between. And then the shortest it can reach, or the closest to this origin, is going to be this length minus this length. And so typically planimeters try to minimize this difference so that you can reach basically anywhere even with inside this near the origin. And so this creates sort of a donut type shape, which I'll show above. And now let's take the tracer arm by itself because it has two more components that are worth talking about here. Let's get rid of the pole arm. And one of these components is this tracer wheel right here. Now, in this prototype, the wheel doesn't actually spin, but in a traditional planimeter, this is the wheel that would be spinning and the wheel that would be actually doing all of the calculation for the area. And so we'd also have a dial that reads how much the wheel has spun. This planimeter, as we're going to see later, sort of imitates that in a digital way. But you can imagine that this is just a normal wheel that's rolling, and then this is a counter for how much that wheel has rolled. And then the final component is this just little tracer tip. And this could either be sort of a pencil. In this case, I just have a needle. And this is what we actually use to trace around the shape. So in the end, if we put back together our pole arm and our tracer arm, then we can show a little demonstration of how one might use a planimeter. And so we can draw a little shape here, let's say something like this. Not the easiest area to calculate. And then fix with our trusty paper clip the origin. And then what you would do is essentially use your fingers to go around this shape. And the wheel would be rolling. And then once you close the curve of this shape, you would read at the end the area of that. And I'll show you this a little bit later with this planimeter. But again, you can just imagine that we have a real wheel here and this which shows the area calculation after we're finished. And so now let's talk about why that actually works. What is the math behind it? And then finally, we'll do a little demonstration with this planimeter to show that it works in a similar way as your traditional planimeter. So to talk about the math of how a planimeter works, I'm first going to label the parts in this physical planimeter, and then we can turn to a simulation, which will better show, hopefully, some of the intuition behind why a planimeter works. So we're going to call this base here O, which is the origin of our planimeter. We're going to call this angle that it makes with the x-axis. So you can imagine there's two axes here. I'm going to call this angle alpha. So alpha right there. This is going to be labeled as length L1. And then we can do this maybe a little bit here. Imagine that we have just a parallel axis. And so this angle here is going to be beta. Hopefully you can see that okay. And then the point where the tracer wheel is, right here, we're going to label P. Let's label this rotation joint M for our midpoint. And finally, this T for our tracer point. And then the distance of this whole tracer arm is L2. And then finally, we want one more distance just to keep in mind and to label, which is the distance between M and P. And so let's call that distance S right there. Okay, so now we can turn to our simulation and see how this works. Here is the simulated version of the planimeter we have just seen. We can turn on the trace and draw a little enclosed curve. And while we trace the curve, take a look at the bottom panel. The planimeter is constantly updating our wheel roll, which we will call W here. Now, this variable W can be a little confusing because it isn't measuring rotation in degrees, but it's instead measuring something called signed rolling distance, which you can think of as tracking the distance covered by a point on the rim of the wheel, purely by the rolling motion of the wheel. When the wheel is rolling forward in the direction of the wheel's normal vector n, W increases, and while the wheel is rotating backwards, W decreases. If the wheel slides without rolling sideways along the axis perpendicular to n, no roll accumulates at all, and so W remains constant in this case. So while W is directly proportional to how much the wheel rotates, it's important to remember that W is a length, not an angle. You can also see the angles alpha and beta changing, but that's really for demonstration purposes. In a real planimeter, we would not have access to these angles, only to the total assigned amount that the wheel has rolled. And this idea that we can somehow get the area from this variable W is the core idea that will guide our proof. To then get this total assigned rolling distance W, you can imagine that every time we move the tracer arm just a tiny bit, the wheel rolls a tiny signed step dW. Adding up all of those infinitesimal steps along the entire curve gives us W, which we can express as the closed curve integral of dW. And at each infinitesimal step dW, it measures how far the wheel moves along its normal vector, n. Mathematically, we can write this as the dot product between our normal vector and dp, which is the tiny displacement of the tracer arm. The dot product here is essentially extracting the tracer arm movement that actually causes the wheel to turn. It's filtering out all that sliding movement perpendicular to the wheel and just capturing the pure roll. First, and this will help us build up to the next step, notice how alpha and beta adjust as we trace the curve. They play slightly different purposes, though it's a bit hard to see since most of the time they are adjusting to reach a new point. But in this simulation, I can change them separately, and we can get an idea of what each one does. Sweeping alpha rotates the main pole arm and changes what regions the tracer arm can reach. Rotating beta, on the other hand, pivots the tracer arm, which allows us to navigate around more fine edges and local details. The position of our tracer point T and wheel mount point P can be expressed in terms of alpha and beta. To express the point P in terms of alpha and beta, we can first express this midpoint M as L1 times the vector cosine of alpha as the x component and sine of alpha as the y component. Then we can take that and say that, well, we'll change colors here. P is equal to then M plus S times the vector cosine of beta this time, and sine of beta as the y component by the same logic. We can express this unit vector cosine beta, sine beta as a unit vector u in this case, which will be perpendicular to our normal vector. And so we can draw it here. It's just the vector that goes along in the direction of the tracer arm. And so if we simplify that out, we can say P equals M plus S times this vector u, which is in the direction of the tracer arm. Then if we take the derivative of P, dP, which is that tiny nudge, this is dm plus S du. Okay, so I've just rewritten this at the top of the screen again, so we have a bit more space. And now we can take the derivative, and we first can start with the dm, which if we take the derivative is L1 times the vector negative sine alpha, cosine of alpha, d alpha. And if we take the derivative of this unit vector in the direction of the tracer arm, then that's going to be negative sine of beta, cosine of beta, d beta. If you look at this du term, we can see this negative sine beta, cosine beta is actually going to just be the same thing as our normal value. And the reason for this is if we take the rotation matrix of pi over 2 degrees and apply that to u, then we just get our normal, which is, again, facing in the direction of the wheel. So we can simplify and then say du equals n times db, and then finally plugging this back into dp, we have dm plus then this little term SN dB. And we're going to go ahead and write that on the top again, just so we have some more space to work out the next steps. So now we can use this dP term in our dW term, which is the little bit the wheel rolls every time the tracer arm moves. And if we replace our dP term in terms of alpha and beta, we can see that we get n dotted with this entire dP term. And then we can distribute this out and are left with this simpler expression that essentially says that the amount that our wheel rolls, the tiny amount that our wheel rolls, can be expressed in terms of two components. The component that changes with the tracer arm and the component that changes with the pole arm. And so the first term is the pole arm movement, and the second term represents the tracer arm movement and how those contribute to moving the wheel just a little bit. We are now getting to one of the most exciting points of the proof, so I hope that your heart rate is at a relatively steady rate. And so we're going to turn on this sweep button right here in the corner. And we can see now that when we drag our planimeter around, the tracer arm is sort of acting like a paintbrush and sweeping out area. This area that it is sweeping out, we're going to call our signed area. It's signed again because the sweeping perpendicular to the arm in the same direction as the normal collects positive area, while sweeping in the opposite direction collects negative area. Wherever you see gray regions, that's where positive and negative areas have canceled each other out to zero. If we go ahead and turn this trace on again, something really beautiful happens when you finish tracing a closed curve. So at first, this swept out area looks kind of chaotic and spans far beyond the loop. But as the arm moves along the back half of the curve, all of that extra area outside the loop sweeps in the opposite direction and cancels it out to zero. And so what's left behind is this purely signed area only inside the curve. And taking the absolute value gives us the exact area of the shape, which means that critically, if we can calculate this total signed area, then we can find the area of any closed curve. To then connect our swept area back to our signed rolling distance, let's look how a tiny change in d alpha and d beta sweep out the area. First, if we change alpha by just a little bit, you can see that a little parallelogram is swept out. The base of the parallelogram is just the length of our tracer arm, L2. The height of the parallelogram is going to be perpendicular distance to the amount that the tracer arm moved, which is what we just calculated, dW. Since d beta is 0 in this case, then we can just ignore that term here. And so ultimately we get that this dA slide, so the little bit of the parallelogram slice, equals L2 times our normal times dm. Likewise, if we change beta by just a little bit, you can see a tiny wedge is swept out. The area of a circle is pi r squared, and r in this case is L2, but we only sweep out an angle of d beta, so we have to divide by 2 pi radians and then multiply by d beta. And in the end, we get this term 1/2 L2 squared d beta for the area of our circular sector here. In total then, when we move our tracer arm just a little bit, the tiny area that is swept out is the addition of the parallelogram, so the area swept out by rotating the pole arm, and the circle sector, which is the area swept out when you're rotating beta. And so now with a little manipulation, we can express this tiny bit of area, dA, in terms of dW, which will help us plug in what we already know. And so we end up with this term here where d area equals L2 dW plus this term times d beta. Then to get the total area, we have to add up all of those infinitesimal bits of area as the tracer goes along the closed curve. So simplifying, we get these two integral terms. First, L2 times the closed curve integral of dw plus this term times the closed curve of the integral of d beta. So for the first term, the integral over this closed curve of dw is just the very first equation we started with, which simply resolves to the total sine distance of the wheel roll, w. The second term, though, is a little bit trickier. So what is the integral over the closed curve of d beta? Let's see if we can figure it out by going over to the simulation again and seeing what happens to the angle beta when we go over an enclosed curve. It actually ends up in the exact same position as it was. And so the planimeter was designed so that after tracing around a closed curve, the configuration is the exact same in the beginning and at the end, which means that this term is simply just 0. So we can cancel that out, and in the end we have this shockingly simple result, which is that the area of the enclosed shape is just L2 times the wheel distance roll term. Now there is one special edge case to keep in mind, and that is what happens if the planimeter anchor point sits inside the shape we're tracing. So when the arm loops completely around the anchor point, which I can't quite show here, it sweeps out a full 2 pi radian circle. This creates a constant offset known as the null circle, which is a baseline area that the wheel fails to register because the arm just spins in place without rolling. So to get the true area back in this scenario, you just have to add this fixed null circle constant back into your final result. And physical planimeters will often come with a table or a constant stamped right into the casing to tell you exactly how much area to add. If you made it this far, thank you so much for watching. As mentioned, the simulation and the proof will be publicly available online, and I'll link it in the description below. And now you know what to do if you ever encounter a situation, which inevitably will happen, where you have an area that you don't know how to calculate. You simply can go onto eBay, order a original Amsler planimeter, wait 5 to 6 weeks or months, and you will be right on your way. Thank you again and have a great day.